Good afternoon. So we've looked at taking the derivative using first principles, and we've looked at our power rule, our chain rule, our product rule, and quotient rules. And now there's this thing that we can go a little bit further with where we take further derivatives. So second and third and fourth and beyond derivatives of functions. So in function notation, we talked about f of x, and that's the same as y. The derivative of that would be f prime of x, or dy dx, but that's a function, and we could find the derivative of that. We could take the derivative one more time. That's going to be called the second derivative, denoted as f double prime of x, which is equivalent to d squared y over dy squared, dx squared. And that's, again, going to be a function, so we could go a step further and take the derivative of that again. F triple prime of x equals d cubed y dx cubed. And we could go on and on and on, but usually after the f triple prime, we start just using a number as the exponent. The fourth derivative of x, the fifth derivative of x. And we could continue taking the derivative of this function over and over and over again. Now, why do we care? Well, we'll get to that, but let's do a little bit of practicing first. We're going to find the first 5 derivatives of f of x. So pause the video right now, find the first derivative. Our first derivative would be 4x cubed minus 6x plus 2. Now we'll take the derivative of that. The second derivative is going to be 12x squared minus 6. Third derivative, fourth derivative, and finally the fifth derivative. Find these other 3 derivatives right now. The third derivative is 24x. The fourth derivative is 24, and the derivative of that, the fifth derivative, is just 0. So there's our first 5 derivatives of x to the fourth minus 3x squared plus 2x minus 1. And now you're wondering, okay, great, we can take the derivatives, the second derivatives, yada, yada, cool. Why? Well, it so happens that position, velocity, and acceleration are related through derivatives. S of x is the position function, and it's measured in like meters. And if we differentiate this with respect to time, I guess we can call this S of t, we get distance divided by time. What we get is the velocity function. The rate of change for position is velocity. If we differentiate velocity, what do we get? Well, what's the rate of change of the velocity? That's the acceleration, people. So S of t is the position function. Its first derivative is the velocity function, and its second derivative is the acceleration function. So find the velocity at time equals 2. Well, velocity v of t is equal to the first derivative of the position function. So 3 plus 10t minus 3t squared. That function will tell us the particle's velocity at any given time t. And what I care about is v of 2. And if I substitute 2 into this derivative, into this velocity function, I get 11. It'll be measured in centimeters per second, or we could also say centimeters second to the negative first. Now we want the acceleration at that instant in time that that particle is moving. Well, that's going to be a of t, and that's found by taking the second derivative of the position function, which is going to be 10 minus 6t, a of 2, the acceleration at 2 seconds is negative 2 centimeters per second squared, or similarly, the units could be written as centimeters second to the negative 2. So there we go. There's an application for our second derivative related to motion of a particle.